Um, okay, guys, we'll get started. So I'm just going to ask the people that are walking in right now to just walk in just a little bit quieter so we can get started. So I'm Nyalle Morosi, and today I'm going to introduce our next speaker, Moustapha Cisse, who is a research scientist and a team lead of the Google AI in Ghana, which I think you guys must have seen these announcements on Twitter and in other media. Moustapha is also a professor of machine learning at AIMS. Some of you here are probably from AIMS, which is the African Institute for Mathematical Sciences. He's also the founder of the African Masters in Machine Intelligence, which is a program that will start in 2 weeks in Kigali, Rwanda. Also, some of you here will probably be going to that program. Additionally, he is a co-founder of Black in AI, which held its first workshop last year at NIPS. And the aim of Black in AI is to increase representation of Black researchers in AI and machine learning. Before joining Google, Moustapha was a research scientist at Facebook, in the Facebook Artificial Intelligence Research Fair. In his research, Moustapha is committed to building an axiological machine learning, machine intelligence to improve societies, especially the societies that are underrepresented. I think the first part of this is proof of this work and this passion. He was born and raised in beautiful Senegal. If you haven't been there, do yourself a favor and go. I have, and it's as lovely as it is. I can attest to that. And he studied, his undergrad was in mathematics and physics at Université Gaston Berger in Saint Louis. After that, Moustapha went on to complete his PhD in machine learning at Université Pierre et Marie Curie in Paris, France. All the French people, I would like to apologize for my butchering of the language at this hour. Thank you. Ladies and gentlemen, please, Moustapha.
It's okay. Thank you, Nyalle, for the intro. It was, you got some bonus points for the French pronunciation. This lecture is about foundations of deep learning. It's actually interesting that Nando covered the grand scheme and basics, which will allow us to just dive deeper into some of the details of the topic. So we're going to start by looking into the problem of learning. So in general, the problem of learning is posed in this way. We have a distribution of data, probability distribution of data, right? Joint distribution between X and Y's, where X is the set of inputs and Y is the set of outputs or targets. And what we're trying to do is to learn a function, a mapping between the inputs and the outputs, right? So in order to do that, we need a measure of success, which we call criteria. And ideally, we measure the success directly on the data generating distribution, right? And the term for that is, for that measure of success here is generally called the risk. And because we don't know this data generating distribution, which is generally nature, if you think about natural images and all of those things, we have just access to a sample, data sample from that distribution. So we measure success on that sample, and we work with what we call empirical risk minimization. Right? So this is just a classical setting of learning. And we assume, of course, that the data is independent and identically distributed, which is the back learning assumptions. And the function that we are trying to learn, this function that we're trying to learn here, depending on the nature of this function, we will be saying that we are doing deep learning or something else, right? In fact, when this function is a deep neural network, then we are doing deep learning. It's as simple as that. So, this lecture is about the foundations of deep learning, right? Foundation. What is deep learning built on? And the foundations of deep learning are actually shallow learning, right? So, even though this lecture has deep learning in its title, it will be more about something else than about deep learning. Because deep learning is just a class of function, and it builds on a very long history of machine learning, different learning paradigms with simpler functions. And then what we will see is how what deep learning brings on top of that, and how it improves upon all the existing machinery. So we'll start with very simple things. So we will start here with something that I believe we all know. Hello? Basic linear regression. So in linear regression, what we're trying to do, similar to the initial setting, we're trying to predict a set of outputs with our inputs, with the particularity here that the function that we're trying to learn is linear, and our measure of success, the criteria, is the mean squared error. So the problem can be written this way. It is generally convex. I mean, I should put this in brackets because it's not necessarily true. And when it is, you can solve it very easily and find because it is convex, you can find one global minimum, right? So before we move on, right? How would you solve this problem, right? What's the simplest way of solving this problem? Anyone has an answer? Okay, so analytical solution, perfect. It's interesting that you say this because most of the time now, actually a few years back, if you ask this question, people will answer this. But now, if you ask this question, people will say gradient descent, which is actually quite interesting. Yes, so this is the natural solution of this problem. But this has there is an issue here. There is a caveat here. So what's the caveat here? Yes? Sorry? Okay, so that's one thing, but we'll come back to that. Yes? Okay, so the inversion. So this, in fact, it may not be invertible, right? So when this is not invertible, what we usually do, so the problem is ill-conditioned, we cannot solve it analytically if it is posed this way. What we usually do to be able to solve it analytically is that we regularize it, right? So if we add a regularizer this way, now what can we do? If we want to solve it, we just compute the same analytical solution, but this time the solution always exists if lambda is larger than 0, right? If lambda is strictly positive, the solution always exists. Okay? So now we found a solution for the conditioning problem. So now we have a second problem which he mentioned, which is that since we are now in the era of big data, so we have a lot of data, and the data is most of the time very high dimensional if you're working with images or genomics data and all type of data. Actually, you may have data living in very high dimensional spaces. Inverting this matrix is actually quite expensive, and sometimes it's prohibitively expensive. So you don't want to do that, right? So what's the solution to this problem? Someone has a solution? Well, gradient descent. Of course. Right? So when we can't find an analytical solution to a problem for various reasons, we seek for a numerical solution. And our preferred algorithm for finding a numerical solution for such large problems is actually just to do, in fact, stochastic gradient descent instead of just batch gradient descent. So how it works, we can just rewrite the criteria. So the last function decomposes on the data, right? So when we do that, simple calculus, just take a first order derivation, write the equation equal to 0, and then what you end up having is this update rule. I'm sure we all know this, right? Okay. So now the problem is much simpler. And what we have seen here is that we initially had a problem with ill conditioning, and the solution we employed was regularization. And then we had another problem with the scalability, and our solution to this problem now is to use stochastic gradient descent, right? We have found two tools that will be very useful in the next steps of this lecture. Great. So is there any question at this point? Okay. Good. So here is another reason why we may want to use stochastic gradient descent, right? Even when our problem is seemingly well conditioned, and even when our data is not that large, sometimes we are interested in problems where the criteria, the proxy we are trying to optimize for, does not allow a closed form solution, right? So we previously talked about linear regression, which is very handy if you're dealing with regression problem, but most of the time, if you work with classification problem, you want to use something else, a better proxy. So let's say logistic regression. This problem is definitely convex, and it's actually smooth and convex. So you know there is a solution. There is one global minimum, but you cannot find it. You cannot find a closed form solution to this one. So you can only find a solution by using stochastic gradient descent. So when the problem is complete, when the function you're trying to optimize or the criteria does not allow for an analytical solution, then decomposing the problem this way and solving for stochastic gradient descent can also be very, very helpful. Right. So what we know now is, for classification, we can use linear regression with SGD. For regression problems, we can use, for classification, we can use logistic regression. For regression problem, we can go with linear regression. And in both cases, we can use SGD and then regularize our models to improve the stability. So the question now that comes to mind is actually, why do we need neural networks, right? If we have something that works really well for classification and something else that works really well for regression, and we know how to optimize it in almost all situations, so why do we ever need neural networks? So what's the answer to this question? Yes? Doesn't always? Why? Okay, good. So there we go. So here is an instance of such a complex problem. So for this problem, for example, you cannot find a solution with a linear model if you work in the original feature space, right? So if you work only with your original data, you can run your logistic regression with any regularization you want, you will never find a solution. This is a XOR problem, and this is one of the motivations, at least an illustrative motivation of using neural networks. In fact, previously, here's one thing people used to do, which is you take your data, you do some pre-processing to the data that makes the data that was previously non-linearly separable, it makes it now linearly separable. And this pre-processing goes, this function phi here. Oops, I don't know if you, yes. And you know, this is one way of dealing with this problem. And it actually was very popular for a long time in the community. In fact, most of the papers published at NIPS or ICML between 2000 and 2008 or 9, many were dealing with finding new functions phi for specific problems. But this is very painful, and I know at least a couple of people who used to work with kernels. If you don't believe what I'm saying, just ask them. There are some people who have spent a lot of time doing this, and it's very painful, and you have to come up with a new kernel for every type of data, and you have to ensure some properties for those kernels to work the way you want them to work. You have to make sure they're positive, semi-definite, the immersive kernels, etc. Very complicated stuff, and doesn't always work, right? And then here comes the neural networks, right? So instead of now trying to find manually hand-engineered features that makes your data separable, you just take your data as it is and throw it to neural networks, and it automatically learns the features, right? Just works directly. And this is possible because a long line of theory has shown that neural networks are actually universal approximators, which means that if you have a real function, a mapping from a bounded domain to R, you can arbitrarily closely approximate it with a neural network, which is a very important result, because it means that the only limiting factor is how big can the class of function that you want to search in, how big can you afford that class of function to be, right? If you can allow it to be very large, which is just a very big neural network, then you can approximate literally any function. So the real problem now is how to search for big classes of neural networks. Yeah. So what is all this about? So neural network, if you look into it, it's just a composition of function, right? It's especially feed-forward neural network. It's just a composition of function. You have different layers that you stack on top of each other, and every layer is a function that transforms the data and feeds the transformation to the next layer, and you iterate the process until you reach the last layer of the model. Right? And similarly to previously, you still have your criteria, your loss function, which is depending on whether you're doing regression or classification, you will be using something like mean square error, or doing logistic regression with the logistic loss at the end of the model. So the only difference here is that you're stacking different functions, and these functions are actually nonlinear. So the two main nonlinearities that we used to use in the recent past are actually the hyperbolic tangent and the sigmoid. These were the most popular activation functions. So once you can stack those layers and you have a lot of data, the only thing that you need to do now is just stack as many layers as you can, right? Just take your problem, and then the more layers you stack, the better it seems to be. And this seems to evolve with time, actually, because in 1998, there was just 5 layers in LeNet, which was at the time doing quite a good job. And recently, in the residual networks paper, there are models with 1,200 layers. So just go deep or go home, as they say. It solves all problems. So here comes the problem. If you have a lot of data and you can just stack these complex functions, complicated class functions, then how will you train them actually? That's the problem, because training a model is just searching for a function in a very large class of function. And the deeper your model is, the larger the class of function you're searching in, and potentially the more difficult that search is. So can we just use the traditional machinery that we knew from before to perform this search? And what we knew before is actually, we knew that if we have a complex function and a problem for which we can't find an analytical solution, we seek for a numerical solution, and a great way to do that is stochastic gradient descent, right? So we are going to do exactly the same way. Yes? I think you are close to understanding what's going on here. Yeah. Continue in that path. You're very close to understanding what's going on. No. So I think there are two answers to your question. So first of all, why do we need depth? Okay? I didn't go into more details, but there are theoretical results showing that there are functions that if you want to approximate them with a shallow model, you will need exponentially many more parameters than if you use a deeper model to approximate them. So yes, so those results do exist, right? There are also recent results showing that sometimes optimizing a deeper model, not just because of hardness, right, but just from a purely optimization perspective, optimizing deeper model is simpler than optimizing shallow model because of the landscape of the function. So, but this is theory, right? And as we know, theory is theory. Okay. It's sad for the rest of us, but yes. So now to answer your question more directly, why 1202? So this paper, Residual Network, the main author of this paper, who used to be my colleague, is Kai-Ming He. He knows how to pick these numbers. So this requires a lot of parameter search, hyperparameter search, etc., etc. So there is no magic here. People are used to train these models, and they get, I should say, familiarity with the way they work. And if you can train them and you can stack more layers and can afford the compute to train them, then you just do that until your performance stops increasing. Right? But model selection itself in neural networks, it's a very active topic of study. So I don't know if you have recently followed, there's a whole line of work on hyperparameter search using bandits, using reinforcement learning. There is all this trend on AutoML, learning to design the architectures themselves. It's a very important line of work. It's part of the science here. Yes. Yes. So that's why they say go deep or go home, right? So for now, go home means 1,000 layer, but in 5 years, you will go home much later. So, Anyways, so we know how to train. We have built on what we know from linear models, what we know when we don't have analytical solutions. We know that in that way it's recommended to do stochastic gradient descent. We also know that regularization works really well, right? At least it helps a lot, conditioning, etc. There are other motivations for regularization, which is it reduces the class function, the size of the class function that you're searching for. But for neural networks, in fact, there are a lot of additional tricks. In addition to the ones that we have seen before, there is a lot of additional tricks, and that's what we are going to see now. Yeah. So, I think the key ingredient in training neural networks, it's unfortunately more and more people don't know about this because you have TensorFlow, which is good, which is really great, but at least you need to see this once and implement it yourself once from scratch if you really want to know what's going on under the hood. And it's backpropagation. It's a very simple, doesn't require any complicated math. It's just a simple application of the chain rule. So you write down the function of a neural network, which is, again, a composition of function. And to update the parameters when you do stochastic gradient descent, you need the gradient with respect to every parameter. But the gradient with respect to parameters in a composition of function is just given by this formula right here. And every element in this formula in a neural network, in a feed-forward neural network, can be computed just with one forward and one backward pass. And it's given by this second formula here, right? This one. So it's a very simple procedure. I'm not going into the details because I think it would take too much time, but I really encourage everybody here to just go and implement it from scratch at least once. And then once you've done that, you can start using TensorFlow. You gain the right to use it. Right? So the forward pass is just the repeatedly applying the different layers of the model until you reach the output. You apply the loss function, and then you calculate the gradient of the loss function with respect to the outputs. And from that point, the gradient of every parameter from the model depends only on the gradient of the parameters that comes before when you go backward, and the activations or the values of the parameters at the layer where you are, right? It's an iterative, repeated process, and based on a chain rule, it's very simple. But it works, at least, implementing it once. Any question? Okay. So, backpropagation is not the only new tool in the set of tricks that people use to train neural networks. Here is another one, which is dropout. So dropout is important more for historical reasons, because it's the regularization procedure that allowed Alex Krichevsky and Geoff Hinton to train the model that won, the first neural network that won the ImageNet challenge. And that model changed a lot of things in the field. It's a very simple procedure which consists in setting a probability P with which every neuron in the neural network is dropped out, which means it is just zeroed out while training. And at prediction time, all the activations are now multiplied by P. So dropout can in fact be understood as being training an ensemble of models, implicitly an ensemble of models. And it's very useful in some cases for preventing overfitting and helps a lot with optimization. So here's the explanation they gave in the paper, which is that dropout prevents co-adaptation between the hidden units. So since the paper has been released, there are a lot of papers that came after this one and provided many different interpretations of this technique. And in fact, for linear model, you can show that dropout is almost equivalent to some sort of L2 regularization because it's just adding noise to the input. For deep neural network, it's a little bit more complicated, but it's doing something far from that. So in practice, when you train a model with dropout, the type of features you learn are very localized. You tend to see features that are very localized, look more like Gabor or filters. So this is a visualization when a model is trained with dropout and when a model is not trained with dropout. And you can clearly see that the features here are way more localized. Okay. So there is a bunch of other regularization procedures out there other than dropout. You have batch normalization, which is standard in almost all architectures now. Drop connect, which appeared at the same period as dropout, but which is not as used as dropout. You have layer normalization, which is kind of similar to batch normalization, but more on the weights of the model. You have other, a little bit more involved approaches like spectral normalization. There is also a recent regularization procedure called mix-up. I have tried it. It works really well. And there are many other regularization procedures. This is still a very active area of research, how to regularize a model so that it learns faster and generalize better. If you're interested into looking into new ways of doing this, it's a very interesting. Sure. Yes, it is. You're absolutely right. So his question or his remark was that stochastic gradient descent itself is a form of regularization. It is right. In fact, if you train a model, if your model is not very complicated and you train it only with stochastic gradient descent, you can show that it finds the solution with the minimum norm, which means that it is implicitly regularizing the model. So these are new results. In the last 2 years, there is a lot of work that came out on these things. It's implicitly regularizing the model in many ways, yeah, definitely. Yeah. Yes? Oh, this is... Okay, so there are a few interpretations of why it works. So one is that, so what mix-up does, just to clarify so everybody knows. So what mix-up does is instead of training on single examples, you take two different examples with their labels, and you take a convex combination of the two examples, and that as target, you take the convex combination of the two targets, which means that if you train a model with pictures of cats and dogs, instead of showing to the model a picture of a cat or a picture of a dog, you take a picture of a cat and multiply it by 0.3 and a picture of a dog and multiply it by 0.7 and ask the model to predict that this is 30% of a cat and 70% of a dog. I don't know what's the name of that creature, but it can be interesting. So your question is why this works. So there are a few explanations. Intuitively, it works because it is enforcing smoothness. If you take a linear model and you write it down, you can derive the equations. You can show why it works. It's clearly a regularization, both in the input and in the output space. But if your model is nonlinear, what happens is a little bit more complicated because it also acts on the second-order derivatives of the model. So it enforces smoothness somehow in the function that you're learning. But that's one explanation. There are a few other explanations. We can have this discussion offline if you want. Yeah. So I know this method because one of my intern actually invented it last year. So, yeah. So another line of work that actually improves deep learning beyond the regularization is new optimization procedures, right? Because the neural network, especially when it is very big, so when it is thousands of layers, it's a non-convex function, very complex landscape, and it's very difficult to optimize. So one line of work, something that people have invested a lot of work on, is designing new optimizers to improve the performance of the models. And among the many optimizers that do exist today, if there was one that I think should all know about, is probably this improvement of stochastic gradient descent, which is the momentum. And what momentum does is it just adds inertia in the direction that stochastic gradient descent would take. And the reason why this is interesting is because when you're doing non-convex optimization, your solution depending on how difficult your problem is, the solution depends a lot on two factors. One is your initialization, and the second one is the learning rate, so the step size. At every step, how far do you go in the direction of steepest descent, or an approximation of it? And momentum reduces that dependence, because that dependence can be problematic if the landscape of your function is chaotic, right? When you have narrow valleys and all that. We'll see it in the pictures. So what momentum does is, instead of doing the update directly on the gradient, you keep some historical terms that account for this change. So instead of directly having the update as previously, now you have this U, which you update, and then the update on the parameters W depend now on the update on the values of the momentum. So if gamma is equal to 0, it's exactly stochastic gradient descent. But if gamma is larger than 0, it has two main effects. One is that it accelerates the learning procedure when the gradient does not change too much, right? And when you're in narrow valleys, what happens with momentum is that it dampens the oscillations. So here's what happens. When you have a large learning rate and your optimization progresses in narrow valleys, when you use stochastic gradient descent, you have a lot of oscillations, right? And this typically slows down a lot your learning procedure. But when you use momentum, what happens is this, right? So it reduces the oscillations and accelerates the learning. It's very useful. In general, it's something to usually try by default when you train your models. So, because people in deep learning are fancy, they have many different optimizers with many interesting names: Adam, Adamax, Nadam, Ada Delta, Hermes Prop. And the last one is particularly interesting for theoretical reason. In fact, this is the way neural networks should normally be trained, with natural gradient, at least from an information theoretic perspective, but it turns out that it is too expensive, so we cannot really use it practically. But making this algorithm practical is actually subject of very active research, and there is a lot of interest around this, because if it was practical to use this, then it would solve just many problems. Natural gradient. Okay. Good. Any questions? Yes? Very good question. You try them all. No, don't do that. in fact, so there are some rules of thumb, right? So starting with stochastic gradient descent and momentum is always a good bet, right? It's always something you can try. It's very difficult to beat unless you're working with some specific problems. Now, when you're working with sparse data, let's say you're working with text, right? Let's say you're doing language modeling, or you're doing machine translation, or this type of things, where the distribution of your inputs, or which are embeddings, or the distribution of your outputs are actually power law. So you see some of the features way more often than you see other features. In that case, you need an optimizer that accounts for that, right? That when it doesn't see one feature very often, whenever it sees it, it updates it proportionally to the number of times it has updated it before, right? Or inversely proportionally to that. And that's typically what approaches like AdaGrad or Adam or Adamax, that's what they do, depending on the norm that you consider. So there are various rules of thumb. If you're dealing with sparse data, then it's good to explore these more advanced optimizers. Otherwise, if you're working on vision data, then usually doing SGD with sometimes momentum is definitely what you want to do. Any question? Okay. So this is also an active area of research. People have derived a lot of new algorithms. I'm sure by the time we finish this talk, there is one new algorithm which have popped up on arXiv. So yeah, it's very difficult to keep track of all these things. So another interesting ingredient that makes these models work, in fact, I believe the impact of this one is underestimated, is the type of activation function that we use. So before, we were mainly using hyperbolic tangents or sigmoids, etc., but now we use rectifier linear units, right? What are these rectifier linear units? They're non-saturating activation functions. So so the rectifier linear unit is in red, and the hyperbolic tangent is in green here. So if you look at the rectifier linear unit, it is a non-saturating function, and for that reason, if you take the gradient of the activation function, it doesn't vanish. While if you consider the gradient of the hyperbolic tangent, it vanishes. If your neural network is very deep, remember that when you do backpropagation, you compute the gradient at every step and pass them to the next one. So if the gradient of your activation functions vanish, what happens is that the layers that are early in your model, they do not get enough gradient. So you're not learning, once you go, at some point in the optimization procedure, you're not learning the parameters anymore, and you will just be learning on the top layers. So which means that you are implicitly exploring a less powerful class of function, while if you had gradient, you would be adapting those parameters and explore a more powerful class of function. That's why this is extremely important. It has played a huge role in allowing now people to train very deep models. In fact, way more than certain regularization procedures. Yeah. So, here are two other extremely important ingredients. One is a framework that allows you to do automatic differentiation. This is what has allowed people to accelerate their research, because nobody writes their gradients anymore. Nobody except you. You do it once before you before you use TensorFlow. The second thing is the GPUs. The amount of experiment that we can do now is only possible because we have graphics cards that allow us to, yes. Yes. Because it's not never zero. Well, this is a good question. So his question is why we can do this, why we can learn this with stochastic gradient descent, even if the real u is not differentiable, right? And the reason is numerically, it's almost never zero. Like people use various things. They add one epsilon, or in reality, you can use something different than this that gives you the same benefits, like the leaky real u, for example. So yeah. Yeah. That are? I'm afraid they are buried. Yeah. Well, in fact, I should not say this. So recently, I have seen papers mainly coming out from OpenAI exploring evolutionary algorithm for optimizing these functions. But okay, I will tell you my opinion about this. So, doing evolutionary search for optimizing neural networks is literally doing zero-order optimization. That's what it is, right? Doing stochastic gradient descent is doing first-order optimization. So, if you have access to first-order information, why wouldn't you use it? And how on earth can zero-order optimization be better than first-order optimization? I understand that this is interesting and exciting from a research point of view for some reasons, but if you have access to first-order information, then you should definitely use it. At least that's my opinion. If you have what? So what you're saying is that if you have vanishing gradient, then you should be using zero-order optimization, like evolutionary method? Well, it's debatable. I believe vanishing gradient is better than wrong gradient, so, but it's a debatable point, right? Okay, so yes, so we have these two additional ingredients which are equally important. So I'm listing TensorFlow here, but you have an array of automatic differentiation libraries now that allow to accelerate research and software development in this field. And obviously you have graphic cards such as GPUs or even TPUs now at Google. So, to recap, what you need now to train neural networks, deep neural networks, compared to what we had previously, as Nando said before, lots of data, few GPUs, it helps. TensorFlow or PyTorch or whichever software you prefer after you have implemented it yourself. Backpropagation, very important to know. Help yourself with the optimizers, all sorts of regularizers, and this is the recipe that makes deep learning work now, basically. So there are a few things that I did not talk about now, and that you will hear in the other talks, which are, I did not talk about convolutional neural networks. Yes? Okay, so this is a very good question. So I have two answers for this. The first answer is I agree that in general we should work more on designing models and algorithms that perform really well even with less amount of data, aiming at reducing the sample complexity of the models is a tremendously important area of research. And I agree with you that it hasn't received so far the efforts it deserves. That being said, the second part of your question, I will disagree that in Africa there is not a lot of data. Because what I tend to see is that we confuse two things. We confuse web data and data, right? It is true that there is not a lot of web data, but there is a lot of data. A lot. And I will just give you an example. When people now train speech recognizers and all these things, they can go, most of the time, if you're in Europe or North America, you can just go on YouTube, take the audio, the waveforms of the videos, right, and do whatever you want. Okay? So if you do it in Africa, definitely, for many reasons, you will have less data because you find less videos uploaded in the continent on YouTube, right? For bandwidth reasons, etc., etc. But there are areas where you can find more audio data. Every ethnic group in Africa has a radio station. And that's data. In fact, that's a lot of data. But we don't use it. So we should be more careful and look for the data where it is. Because if it's not in the web, it may be somewhere else. Yes? How many? Well, that depends both on your problem and the complexity of your model, right? So if your problem is very simple, then you need a small amount of data. If your problem is complex, then you need way more data. Yes? Okay, this is an excellent question. So he said sometimes we have the data, but it's not annotated. So depending on the task you want to perform, you will definitely need a certain amount of annotated data. It depends on the task that you want to perform. Now, everything around semi-supervised learning and unsupervised learning is also a very active area of research. How to leverage unannotated data to improve the models and how to reduce the burden of annotating data, which can be very costly. I agree with you. This is also a very active area of research, and I believe that any breakthrough or major advancement in this field will be tremendously important across industries and applications in many different areas. So if you're interested in these problems, I encourage you to look into them. Very important problems. Another question? Okay, so yes, so what I did not talk about, convolutional neural networks, which are just some particular parameterization of the layers that allow you to learn better for image data, for example, whenever you have translation invariance and all these kind of things, which can be very useful. You will hear about this from Naila later. I did also not talk about recurrent neural network, which people use to learn from sequential data when you do machine translation or language modeling or speech recognition, for example. I think Cho will be talking about this at some point. I did not talk about embeddings that you can use to infer various things with text data based on the words or embedding for sentences, which can be very useful. And I did not really dive deeper into backpropagation, but I hope that you will look into it. Okay, so now for this part, if you have any questions, then yeah. Yes?
Do you think the research that is ongoing incorporates such complications that come with a problem other than the algorithm?
Yeah, so in many industrial applications, this is a very important problem. So anywhere where you're trying to detect rare events, doing fraud detection, or anywhere where you have these huge imbalances, it can be problematic. If you train your model the way you would train it if your data was balanced. That being said, there are a few tricks that people use to make this work relatively well. One of them is to resample the data while training. Another one is to use what is called cost-sensitive classification, which is you penalize more the model when it makes mistakes on the categories that are rare, right? Other approaches deal with this problem by learning representations that are less sensitive to the imbalance of the data. So there are various ways of doing it. There is research around these topics, and there are various methods. They are not perfect. They're definitely not to the state where the performance are comparable to what you have when you deal with perfectly balanced data. However, there are a few tricks that do work. Yeah. Yeah. When it comes to? Well, actually, I do have a question. Are deep neural networks not as efficient as tree-based models when you have tabular data? Okay, so I understand your point. So in Kaggle, because that's what you mean, right? So in Kaggle, very often, many competitions are won by gradient boosted decision trees and all sort of trees. So there are various reasons for that. So one is you have tabular data, but I think it's more because of the categorical attributes in the data than the fact that the data is tabular itself. And which means that you could overcome that by normalizing your data in a proper way. However, these models, so deep neural networks and gradient boosted decision trees are just different class of functions. And for some type of data, obviously it may be easier to find the solution in one class of function than in another one. And more often than at least from what I see in Kaggle, I see that many people win the challenges by doing this. I have to say that gradient boosted decision trees are much easier to make them work. It's much easier to make them work than to make work neural networks. But what I mean by much easier is that the architecture search and the hyperparameter search, etc., is more complicated for neural networks than for gradient boosted decision trees. So I'm not sure if one is better than the other one for this particular type of data, but yeah, but that kind of model definitely works really well. Yeah. Yeah. Sorry. So, okay, go ahead.
Sorry, in terms of, just out of interest and as much as you can give away, what, in terms of applications, are you guys using deep learning for in Google in Africa?
Okay, very good question. So I will answer one question that you did not ask first, and then I will answer this question. Okay. So that question is, we are recruiting, okay? So if you're doing machine learning and you are interested in working on exciting problems, and Ghana is a very nice country, they have something called jollof. It's a very nice dish. And so if there is some people from Ghana here, in fact, this is very interesting, by the way. This dish, they call it jollof. It's sort of a competition between Ghana and Nigeria. I don't know if you have heard about this. Right? You heard about this? So, yes, so you hear the Nigerian says this is from Nigeria. But bottom line, it's a very, if you haven't tried it yet, you should. It's a very nice dish. But jollof itself, jollof, means Senegal, and that's where the dish comes from. And so, but nevertheless, in Ghana, they make it really well, and that's one of the reasons why you should consider going there, in addition, of course, to work for Google. But now to answer your question, we are interested in a broad range of problems, both more theoretical problems and more applied problems. So from the applied side, we're interested in problems in healthcare domain, we're interested in problems in education, we're interested in problems in agriculture, and we're definitely interested in problems in language. So if you're into any of these topics, just feel free to come see us. One last question, sorry. Yeah. There is a lot of research on this. I myself have done some research on this. I believe it's extremely important for many different reasons, and I have to confess that it's a very difficult topic, because interpreting something, in fact, is very difficult, even for humans. You know, when you ask a human why they did something, most of the time what they will provide is post hoc rationalization rather than tell you exactly what was the motivation of this, or the tell you the consequence rather than saying exactly why this happened. So it's an exciting topic, very active topic of research, but we're very far from models that can provide clear interpretation. There are a lot of people at Google working on these things, and in other companies as well. Yeah. Okay, so last question, sorry.
Hi. So I just wanted to ask, in terms of like concept drift, right, where you have tons of data, but you have that your data points are continuously changing. What would you say is like the best or most efficient way to build a model that's able to pick up those changes, but able to also differentiate between noise and actually relevant data?
What do you do?
I work for apps and I do like data science.
Okay, very interesting question. So the question was, when the distribution of your data changes constantly, what's the best way to keep up with the distribution so that the model stays accurate? So this is certainly one of the most difficult problems people work on in machine learning. Working on distribution drift and domain adaptation is a very old topic, but an unsolved topic. Every day you have new models and algorithms coming out working on these things. There are ways of adapting your model to new data by resampling the distribution, so adding weights that reflect the fact that some of the data are new, some part of your distribution. There are other ways that tackle this problem by learning representations that are invariant to small changes over time. There are other methods that combine non-parametric approaches, which you can make evolve very quickly because you can directly store the data with parametric models. There is a wide variety of approaches that people use to tackle this problem, but it's a very interesting problem, and there is no established solution that everybody uses. So on the internet, for example, you will find people using bandit algorithms, and in different domains, people will be using something else. It's a very interesting topic. Yeah. I'm curious to chat more and see your use cases. Yeah. Okay, thank you.